you saw hopefully you saw the email that on Tuesday, Bruce Johnson will Thursday. No, Wednesday. Hopefully
we'll get it straight next week.
next week sometime.
I don't know. That's what we're getting confused about. The 22nd, Thursday.
Oh, that's a mistake. We better fix that because it's the 21st and I'm not here.
21st is a Tuesday. The 21st is a Wednesday. Okay. So you're not here on Wednesday.
It's the Wednesday class. We'll sort that out tomorrow.
Okay. Yep.
And then the plan is for Ann to teach for a while on tensors and some aspects of solid state after Bruce. When Mike comes back, hopefully, did he have a chance to upload the PDF of these slides and the next problem set? Okay. And after today, I'll upload another problem set just so that we have the first three before Ann using the solid state in our problem set. Now, at the end of class last time, we talked about sampling.
Not going to work today? Of course. We can't get it all working at one time, Mark.
Well, let me try to connect with
That would be too much to ask.
it says there's no Wi-Fi connection. Of course, it is. So we talked briefly at the end of class last time about sampling and this idea that if we are sampling at discrete points, then this theorem called the Nyquist theorem will link the sampling time to the width of the frequencies, the spectral width that we sample after, so that the frequencies run from minus the Nyquist frequency to plus the Nyquist frequency, so that the full spectral width is 1 over delta t, where delta t is the sampling time. So in a 2D spectrum, that will be the increment in t1, and on the Brooker spectrometer, that's usually called IM0, although depending on the pulse sequence, the total sampling delay might be 2 IM0s. Rare cases more. In acquisition, that's called DW, the dwell time. And then we looked at some picture showing what happened to frequencies that were outside the bandwidth, that they get aliased inside of the bandwidth. So the frequencies appear at artifactual positions. Now, one thing I wanted to talk about to finish this is the Fourier transform. The first thing to say about this is if you imagine that we're going to sample from minus the Larmor frequency to plus the Larmor frequency in even increments, when you do the counting, you realize that the Fourier transform of n complex points returns n plus 1 complex points. And that the minus Fn and plus Fn over 2 are the same. So obviously if we have n data points, we can't get n plus 1 unique data points out of doing a Fourier transform. Because the Fourier transform is linear, so it preserves all of the information. So the two edge points are the same, as if the spectrum was connected to make a barrel. And processing programs then throw away one of the points, so that they just return n points of the spectrum when you give n data points in. And I believe it's now the case that all NMR processing software, we can ask Bruce next week, whichever day he shows up, and through NMR effect, that they all throw away the positive edge of the spectrum, so that you actually get back minus 1/2 of the Nyquist frequency up to 1 point less than plus the Nyquist frequency. And that means the middle of the spectrum isn't really where you think it is. The middle of the spectrum is really half the number of points plus 1. So if you have lots of data points, this hardly matters. If you have very few data points, that actually matters in getting the spectral reference frequency. If you think of referencing the center of the spectrum, but the center of the spectrum isn't really the number of points over 2. It's the number of points over 2 plus 1 because of this artifact. Not really artifact, the property of the Fourier transform. If you want to know how your processing software works, just feed in a vector of 1s. And a vector of 1s is just a delta function. Its Fourier transform is just a delta function at 0. And what you'll get back then is a bunch of zeros and 1 point that is non-zero in the NMR spectrum. And then you can look and see, is that non-zero point at n over 2, n over 2 plus 1, or n over 2 minus 1. And then you'll know how your software works. You'll know that non-zero point is n over 2 plus 1. You know that in the future, whenever you reference the quote-unquote center of the spectrum, you should always be referencing the center to be n over 2 plus 1 in order to be completely accurate. Now, the other thing that happens is of course, we don't really do Fourier transform. We do a discrete Fourier transform. And actually, is that part of this? Yes. So, now, here's the continuous Fourier transform. And I've added 2 parts up here from the way I wrote this before. First of all, I've added a phase factor. So this phase factor would be the same across the entire spectrum. And this is what you would call the 0-order phase correction. So when you're phase correcting the spectrum after the fact, you're taking care of whatever phi sub 0 was, just from the nature of the experiment. I've also added this little time delay, T0. T0 reflects the fact that you might not be turning the receiver on exactly at time 0 for evolution of the magnetization in the transverse plane. And there are, absent other effects, there's 2 reasons for this. First of all, if you have a pulse, well, if we're doing just the 1 pulse experiment, you have a 90-degree pulse, you can't turn the receiver on immediately after the 90-degree pulse. There's some ring down of the RF power, And if you turn the receiver on immediately, that power goes into the receiver and distorts the spectrum. So, secondly, as we said, there are some filters in order to cut frequencies out from outside of the spectrum. And filters have something called the time delay or phase delay, and they make it look like acquisition is starting later than you might think. So the combination of the filters and allowing for ring down of the pulse means that there's typically a non-zero tau naught here. And that then looks like a first order phase correction in the spectrum. Because depending on the frequency of a given resonance, during tau naught, a certain phase will be acquired. A resonance that's on resonance with the carrier that won't acquire any phase. Something that's downfield acquires a phase in one direction, something that's upfield acquires a phase in the other direction. So the phase depends on the resonance frequency, and that's what we call the first linear with respect to the resonance frequency. That's what we call the first order phase correction. In many experiments, as you'll see in the next slide, we'll try to adjust this delay. We know there's some delay, and we can, if we want, try to adjust what that delay looks like. We could obviously increase it if we wanted that delay to be larger than it was. We could just add an extra delay period in the pulse sequence before we turned on acquisition for the acquisition, or before we apply the next pulse in the indirect dimension of a 2D experiment. If we wanted to make that delay identical to zero, it means we have to cancel out the evolution during that time tau naught, and we could do that, for example, with the spin echo. We could add a little delay, 180-degree pulse, and then another little delay, and adjust the delays to compensate for T naught. And you'll see examples when I show the spectra of doing that. Why, and you might wonder why bother if you just apply a first order phase correction. And the thing about first order phase correction is that algorithm would basically assume that the lines are infinitely narrow. But the lines, of course, have width, and in particular, the dispersive tails can have quite substantial widths. And that means that the tails of the peak, the dispersive tails, see a different first order phase correction than the center of the peak. And that's not really what you want. You want every peak to see the same first order phase correction depending on what its center resonance frequency is. And the effect of that is that the baseline gets distorted somewhat from the first order phase correction. Many experiments, this isn't so important. You might already be routinely phase or baseline correcting, say, the acquisition dimension of some experiment. And as a result, you might not care if the baseline is a little distorted from a first order phase correction. But other experiments, you might care a lot about the quality of the baseline. And in solution, one of the most important experiments is the nosing. And anyone who's ever done a structure knows that your structure really depends on the weakest peaks that you can quantify. Those are the longest distance. Those are the NOEs reporting on the longest distances that they'll be able to detect. Those are critical for determining the tertiary structure of the molecule, and how small a peak you can distinguish from baseline artifacts depends a lot on the quality of the baseline. So historically, nosy spectra are where spectroscopists worry the most about getting the baseplanes as pure as possible, and therefore trying to correct, among other things, correct for any non-trivial first-order phase correction. As you see on the next slide, they're doing first-order phase corrections that don't have this distorting effect. But in general, they do. And any experiment, really, if you want to try to quantify small signals as opposed to just detecting whether there's a signal there, one should be thinking about how good the baseline is, and that frequently means paying a lot of attention to these issues about first-order phase correction. And
there's another issue that comes up when you have spinning sidebands. They behave differently to another isotropic peak at the same position. And so there's nothing really you can do to get a beautifully phased spectrum except recover that data. So that's another argument in favor of worrying about this. We'll see more about this. And I'm just wondering, because you probably said it right before I came in the room. So the right value for that first point is a little bit of a story for indirect detection. We're talking here about the direct detection.
well, I'm kind of confusing them together. Just saying there is a delay and there are magic values. I haven't really specified what the magic values are.
So that was
please
my
say
question.
a few things.
No, I just was going to ask you to summarize that again. So for the direct dimension, we're looking really for 0 in general for the really broad line spectrum. But indirect is another story, right?
Right, so we'll talk about indirect a little more on that.
But you're looking for 0 is what you're saying here, right? Nothing more complicated than that.
On this slide. Now, there's another consequence of the fact that we sample. We don't measure a continuous signal, we sample at discrete points. And that means that we are calculating a discrete Fourier transform. And that means we've replaced the integral with a summation. And that may seem unimportant, but mathematically it means that the spectra has become periodic. So the discrete Fourier transform of some signal acts as if the signal was periodic. So you think you have a spectrum that looks like this, where you sample various points on it. But mathematically, the Fourier transform thinks you have copies of it going on forever and going backwards forever. And that has lots of consequences. The first consequence is shown here. So we have this summation. We replace the integral by the summation. And it turns out this can be summed. And the sum of this series says that our signal looks like this. That doesn't look very much like the signal we got from the integral. Here's the absorptive Lorentzian. Here's the dispersive Lorentzian. Now, I have this signal, and at least to me, I don't see how that's the sum of an absorptive Lorentzian or a dispersive Lorentzian. Is it obvious to anybody in the audience? So the question is, what would the conditions be that this would be identical to the continuous Fourier transform? And the two conditions turn out to be shown here. The first condition would be that T0, this delay, was identically equal to 0, and we multiplied the first point of the NMR spectrum by 1/2. Now, how many of you, when using NMR play for NMR FX, notice that there's a flag when you use a Fourier transform or apply a window function? The NMR play is -c, and you say 0.5 if you want to multiply the first point by 1/2. Anybody notice that in their processing scripts? Okay,
Well,
look
we're
back
gonna
at-
notice it on the 22nd.
We can't do it. I think the 21st, because that's the day I'm here, not here.
Yeah, Bruce wanted to do the 22nd.
Ah, okay.
Yeah.
That's
what you advertised, right, Mike?
Yes, but
Yes.
we wound up getting confused just as Art came in the door, so we have to.
No, I gave him the
tomorrow.
choice, and he picked the 22nd, partly because I'll be there and work with him.
Okay,
It's not clear that I can do it.
so we have a problem for class on the 21st.
I think the safest thing is to cancel it and promise them that we'll pay them back.
They're looking frightened by that. So that's the first
With interest.
condition, is the initial delay is set to 0. And as I said, that usually will require, at least in solution, and can tell you about tricks in solid state. In solution, that usually will require some kind of spin echo that we can use to compensate. Or the other trick is to set that delay to exactly 1/2 of the sampling time. And then we'll need exactly a 180-degree first order phase correction. Could be minus 180. Depends on details of the spectrometer and the pulse sequence. It'll either be plus or minus 180. One can work out, of course, exactly which one you need for a given experiment. On the other hand, Fourier transform is so fast, I usually just pick one, and if the spectral looks wrong, then I pick the other one. And those two conditions, if we plug those two conditions into this equation, we will then get something that looks like the absorptive and dispersive Lorentz means. Any other values, any other choices for T0 will lead to some distortion away from the ideal Lorentzian line shape after you do your phase correction.
Just another question, it's not about solids, but if you pick the first one, do you think you run into problems because you might be right off on pulse that,
Right, but normally what we would do, for example, here, suppose we were just going to do the one pulse experiment. So we already know, forget about the filters, pulse ring down, whatever, we already know that this pulse behaves as if it were a delta function preceded by these little correction factors. So absent everything else we talked about, there's some phase evolution during the pulse, and we talked about that a few classes ago. Then there's little delays to allow the pulse to ring down and to allow for the performance of the filters. And if you look inside, nowadays Brooker hides all of these delays inside of a macro for acquisition. But if you look inside that macro, you'll see that there are delays that the spectrometer is setting to try to compensate for these effects. It used to be in the old days when we spend a lot of time fiddling with them ourselves. That's become less important with digital filtration. But there's some delays here. So the total time before the first point is acquired is the evolution that happens during the pulse, plus whatever the delays are inserted by the pulse sequence to account for pulse ring down and properties of the filters. So if we wanted to make that 0, what we would do is then add a 180, where here's some delay tau 1 and some delay tau 2, and then we start the acquisition. And then if we make tau 2 equal to tau 1 plus whatever all these other taus are, inserted by the spectrometer, etc., then we'll have perfect compensation. So how one would usually be something pretty short, and we would then empirically adjust how two until we get a perfectly phased spectrum. And at that point, we would know we had compensated exactly. So you'll see, if you look in the NMR book, by Kavema et al., you might notice, for example, a conventional nosy spectrum just looks like this, 3 90-degree pulses, and then a quire. If you look in the NMR book, you'll see that we have a little hot echo, spin echo at the end, and that was to clean up the baseline. So nearly all of the nosy style pulse sequences in Kavema et al. Have this little hot echo on the end. Hot echo and spin echo mean the same thing to me, since the hot echo was discovered by Erwin. I'll use hot echo when I mean just one of these 180. Then use, say, Harper cell, Gill, or CPMG when I mean a train of spin echoes. And then in solids, when you do, again, when you do this on a quadrupole, they both turn out to be 90s.
If it's a weak quadrupole, you can do that. Or if you're refocusing dipole, like if the spectrum is dominated by dipole.
Now, what about this funny 1/2? Where does that come from? And you could say, well, it just comes because somebody figured out that makes this work. Right? So you could just take the attitude that somebody just noticed if we made tau naught 0 and multiply the first point by 1/2, this ends up looking just like the conventional transform. And I think that might have been true when Dennis Porsche, at least in solution, presented this summation for the first time. I don't know if people before Dennis had recognized that we could sum this, but certainly in solution NMR, I think of this being introduced by Dennis. And I think it could be that he just noticed it. Sometimes people claim that the fact that the spectrum is periodic, once you do the discrete Fourier transform, the spectrum is periodic. Think about this. We have some spectrum, and we record it or window it to 0 at long times, and then because it's periodic, it starts over again. And there's a Fourier transform theorem that says that if you have a discontinuity, a jump discontinuity, the transform behaves as if that was replaced by the midpoint. So one might think from just the mathematics of the Fourier transform that this periodicity would mean we should average the last point to the first point, and that would be basically replacing that by 1/2. So, but I think it's actually a little more fundamental than this, and that comes from the fact that our signal doesn't exist before time 0. Right? Before the pulse, there is no signal. So our signal really looks like this, and then suddenly we have a signal, and then you might have been told at some point to 0 fill by a factor of 2. How many people have been told to 0 fill their spectra by a factor of 2? Never? Okay, well, you should always 0 fill by a factor of 2. And If we zero fill by a factor of 2, and then we start over again, and that'll be 0 fill. I didn't want that again. So a 0 fill of the spectrum is periodic. So now, obviously, if I 0 fill by a factor of 2, it's kind of the same whether I think of my period being that, or my period being this. Right? That's all basically identical. I can think of the zeros coming before and the zeros coming after. There's a theorem called and has helped me out, Wiener-Kirchner theorem, Kirchner's theorem, that says if you have a signal that is deterministic, it only exists for time greater than 0, then it has to be composed of even and odd functions. If we 0 fill by a factor of 2, we can make our signal look like it's the sum of even and odd functions by extending back into this time period. So I can extend back into this time period by something that looks like an even extension and something that looks like an odd extension of my real signal. The even and odd extension will add up to 0 in the negative region, and they'll add up to be my signal in the positive region. So by 0 filling by a factor of 2, I satisfy the Wiener-Kirchner theorem, if I'm pronouncing it correctly. And that means I'm Fourier transforming 2 endpoints. I acquired n data points. I 0 filled by a factor of 2. So now I'm Fourier transforming 2 endpoints. I get back 2 n complex points. And then I look at the real part. I look at the absorption part of the spectrum. I'm looking at n points. So I started with n data points. I started with n complex data points. I've ended up with 2n complex data points, but I only look at the n, the real part. So I'm looking at n parts of, n bits of data, as it were. And this Wiener-Kirchner theorem says that I don't need the imaginary part anymore. The imaginary part is now dependent on the real part. All I need to do is look at the real part, and I have the same n bits of data that I started with. Otherwise, you've accumulated 2 n complex points. The real and imaginary parts are independent of each other, so you have 2 n bits of data. If you just Fourier transform that, you would have n complex points. You throw away the imaginary part, you look at the real part, you've thrown away information. You had 2n independent pieces of data to start with. You need to look at 2n independent pieces of data at the end, otherwise you've lost information along the way. And you could say, that's fine, I'll look at the real and imaginary part of the spectrum, but that doesn't get you very far because the dispersive spectra is so overlapped that it's hopeless to look at it. And this trick of 0 filling and then the Wiener-Kirchner theorem says that by 0 filling by a factor of 2, we can move the data so that all the information will be in the real part and the imaginary part is degenerate. And then there's something called the Hilbert transform, that if you have the real spectrum, you can always regenerate the imaginary spectrum exactly from the Hilbert transform. So that's also why, not so much anymore because memory is cheap, when computer memory was expensive, we would immediately throw away the imaginary part of the spectrum after we Fourier transformed it in the same state of space. And then if we needed later to rephase the spectrum, we would do the Hilbert transform to regenerate the imaginary part, rephase the spectrum, and then throw the imaginary part away again to save memory space. Now it's not so critical. Memory is cheap. In any event, once you do the zero filling, then this argument that we have to multiply the first point by a half because of this continuity is correct. Before, it would have depended on, that argument would have said it would only be true if I windowed the function down to zero, bid down to zero, and it actually doesn't have anything to do with that. It really has to do with this zero. I'll upload, this is business about the zero filling, the Hilbert transform, the Wiener-Kirchner theorem is one of these things I can remember for 10 minutes after I review it, and then I get confused about it again. But there's a really lovely internet article about it, so I uploaded that article. It has a very nice picture showing how it all works. If you zero fill by more than one, not by a factor of 2, you're free to do it. But then there's no new information. You can't think if I zero fill by a factor of 2, I now have 2n bits of data in the real part of the spectrum. Why don't I zero fill by a factor of 1,000 and have incredible amounts of information in my spectrum? After a factor of 2, zero filling just becomes a way of doing interpolation. There's no new information. You've just been interpolating between the data points. That can be useful. It can be useful visually to interpolate. But there's nothing magical about interpolating by Fourier transform. You could have zero filled by a factor of 2 and then interpolated by any other technique you happen to like. Curve fitting, splines, whatever. The Fourier transform is easy because the software knows how to zero fill, and Fourier transformation is fast. So it's convenient, but it's not magic. It's doing interpolation at that point. And you're looking like you wanted to add something to that. So I think that's what I wanted to say about the funny parts of the discrete Fourier transform. Next week, it's very easy then to construct spectra and look at the various artifacts that happen if you misprocess the data. But I think Bruce is planning on doing that with NMR FX next week, which will also show you with that software how to generate simulated pre-induction decays that you can play with. So I'll leave that for him and go back to where we were earlier. Slide. So we talked about our first 2D experiment. And in fact, according to the syllabus, we're in fact supposed to be talking about 2D experiments now. So Ann and I, this is probably the 12th time we've taught this course. And I think this is probably the only time that we've reached this part of the semester anywhere near the syllabus. So just to refresh your memory, we had this 2-pulse experiment, and we calculated for a 2-spin system what the signal would look like if both pulses had X phase. And then we realized that was fine, except that the Fourier transform during T1 would generate image peaks. We would have peaks at both omega and minus omega for every signal. And then we realized we could fix that by what was called quadrature detection, in which we went back and did one. Went back, I lost it. Went back and changed the phase of the second pulse, first pulse, to a Y pulse. And then we combined the two signals and ended up canceling the imaging. Now, it doesn't actually, in the mathematics, matter here. Try to find this spectrum again. If you look in a cozy pulse sequence, you'll see invariably that the first pulse here would be the one whose phase would be changed for quadrature detection. So one free induction decay would be recorded when that was an X pulse, and another one recorded when that was a Y pulse, and then maybe minus X and minus Y, depending on the scheme. In the mathematics, it wouldn't matter whether we change this one from X to Y. It'll all work out mathematically the same. It turns out most of the time people do the first pulse, and in fact, if we happen to have a pulse earlier, that might be have its phase changing as well. Because usually, if the pulses before this pulse have their phase changed together, there's fewer artifacts that come up in the spectrum. The saving grace for this, you might imagine, in a complicated 2 or 3D experiment, there might be a dozen pulses before the one that you need to change from X to Y for quadrature detection. And if you look in pulse sequences, you won't see that every one of those preceding pulses have their phase change. These days, it's become less important because gradients are used a lot, which we haven't talked about yet. And gradients tend to suppress these kinds of phase cycling artifacts very efficiently. So this nuance has become less important. But occasionally, there'll be a pulse sequence where it turns out that it is important to phase cycle pulses that come before the pulse, whose phase you really need to change to get the quadrature detection. But in the pure mathematics, it wouldn't matter. That was this to the side. So we had looked at the cozy, and then we ended up pointing out that we had the prediction, our mathematics said that the diagonal would be absorptive and antiphase in both dimensions, and the cross peaks would be dispersive and antiphase in both dimensions. But then conventionally, a phase shift, a 90-degree phase shift would be applied in both dimensions to make the diagonal dispersive and the cross peaks absorptive in order to improve resolution of the cross peaks, which is what we really care about. And then usually we saw in some examples where we would apply window functions. I've lost it somewhere. We talked about applying window functions to try to truncate the tails of the dispersive diagonal. But a huge effort went in the early days to try to do something about the diagonal. And as usual, nothing is free. The good thing about the cozy is it's very sensitive. There's only, back at the pulse sequence, there's only 2 pulses. There's very little chance for relaxation losses other than the relaxation losses during T1 and T2. So it's a very sensitive experiment. As long as the protein isn't too big, the antiphase line shapes tend to be very well resolved in the NMR spectrum. And for something like ubiquitin, and here is the NH alpha region. This is very far from the diagonal, and the dispersive tails are not a problem. So it's a great experiment if you want to look at so-called fingerprint regions that are far away from the diagonal. The problem is when you want to look at the diagonal, and strong window functions to reduce the diagonal are also reducing the amplitude of cross peaks that are near the diagonal. So you can improve matters, but it's not for free. And early generations of NMR spectroscopists worked very hard to try and fix the drawbacks of the COSY experiment. And one of the most elegant ways is called the double quantum filtered COSY. And this is our first pulse sequence that has 3 90-degree pulses. Now, I've already reminded you that the basic NOSY spectrum also has 3 90-degree pulses, and a basic multiple quantum experiment has 3 90-degree pulses. What's called a relay COSY has 3 90-degree pulses. There are a lot of NMR experiments that have 3 90-degree pulses, and one of the issues is how do you avoid having a superposition of all possible spectrum generated by 3 90-degree pulses all at once in your measured spectrum. And this leads then to either phase cycling or gradient selection, in which we want to edit from the universe of all possible spectra that could arise from 3 90-degree pulses. We want to edit down to the subspectra that are interpretable. We want to edit it down to the NOSY, or the double quantum filtered COSY, or the relay COSY. We don't want all of these piled on top of each other most of the time. There are some exceptions. There are, for example, experiments in which you might record at the same time some spectrum where you detect on the amide hydrogens, and an experiment that perhaps you detect on the methyl hydrogens. They're in different parts of the spectrum, the frequency range. So the fact that those two may be very different subspectra, very different kinds of information content, doesn't confuse you because they're just well resolved in the NMR spectrum. Most of the time we're trying to edit down to a fairly simple interpretable subspectrum of all the possible ones. So here we wanted to do a double quantum filtered COSY, and it'll have the issue built into it that we have to edit. Well, first, what is double quantum filtered COSY? And secondly, how do we edit? So here's the pulse sequence. There's a 90-degree pulse, the T1 period, and then 2 90-degree pulses that are as close together as one can get on the spectrometer. And the experiment is done a minimum of 4 times with different sets of phases for the pulses in each case. So the first time we do the experiment, all 3 phases are X, and the receiver is X. The second time we do, we store that in memory. The second time we do the experiment, the first 2 pulses are Y's, the third pulse is an X, and the receiver is minus X. That means we subtract the second experiment from the first experiment. The third time we do it, the first 2 pulses are minus X phase, the third pulse is an X, and now the receiver is an X, so we add the third one to our first 2, and the fourth time The first two pulses are minus y, the third one is x, the receiver is minus x. So we subtract. So we've added experiments number 1 and 3 and subtracted from that the sum of experiments 2 and 4. And the question is, what do we end up with? And we can just do this by brute force. We can do our calculations with our rules 4 times, and then just add up the result, add and subtract the result by brute force, and find out what the answer is. And we, in fact, will do that. But also, a shorthand has been developed to understand what's happening, and these are called coherence transfer diagrams. So I'm showing here, if we have 2 spin 1/2 particles, then the coherences can go from -2 to +2. If we have some operator, I plus S plus, we'll call that a coherence order of +2, the sum of the pluses and minuses. Something like IZ will be coherence order 0, 2IZSZ will be coherence order 0, I plus S minus is coherence order 0. So the coherence orders can be degenerate, but the smallest one is -2, I minus S minus, and the largest one is +2. So I've drawn bars here to represent the coherence orders from +2 down to -2. And then the solid bars represent the subspectrum that I want, what I want to have happen to the coherence orders during the experiment. And whatever else happens on these bars are the subspectra that I don't want. So what happens here? How do we interpret this? Well, I start with IZ magnetization. IZ magnetization is coherence order 0. So I start with the solid line at 0. And now I apply an X pulse. After the X pulse, what's the state? What operator do I have? I start with IZ. I apply an X pulse. I have minus Y, and minus Y is the difference between I plus and I minus magnetization. Minus IY would be I over 2 times I plus minus I minus. So it's the superposition of I plus and I minus, and that's represented here then by splitting the 0 level into a -1 level and a +1 level. I don't know the relative magnitudes of those two. The relative magnitudes of the I plus and the I minus aren't displayed in this coherence order diagram. I also wouldn't know if I had I plus SZ or just I plus, because both of those have coherence order 1. So this picture isn't a full representation of what's happening. It's just telling me about coherence orders. Now during the T1 period, the coherence orders don't change, because all that's happening is IY is turning into IX due to chemical shift evolution, and IX is just the sum of I plus and I minus. And we might be evolving antiphase magnetization, but antiphase magnetization, something like IXSZ, is still the sum of coherence order 1 and coherence order -1. So the pulses can change the coherence orders, but precession doesn't change coherence orders. It just interchanges operators with the same coherence order. And now at the end, here, I have this pulse, And it's now going to spread these coherence orders through the whole, potentially to every possible level. I might end up after this 90-degree pulse with every possible coherence order occupied by some operator. But my experiment, I only want the operators that go either to +2 or -2. So I've shown here the possibilities. -1 could go to -2, or -1 could go to +2. +1 could go to +2, or +1 could go to -2. So I've shown that. And then I have the second 90-degree pulse. It will spread the coherence orders again to all possible levels, or potentially could spread the coherences to all possible orders. But now, my detection operator only picks out -1. Remember, during detection, I'm going to take the trace with the F plus operator, the sum of the plus operators, and the only operators that can survive the trace will be -1 operators. So I get an automatic selection here. So I start at 0, I end up at -1 because of detection. In between, the coherences are being spread through the possible levels, but there's only one or more pathways that I want. I need to figure out how to select out of all possible pathways only what I've shown in the bold lines. And I'll do that by adding up 4 experiments. So in any one experiment, I'm going to have a mixture of the pathway that I want and the other possible pathways. And I'm going to arrange somehow that the sum of the 4 nulls the pathways I don't want and picks out just the pathway that I do want. So is the problem clear? The next may make it. So here, this may help you see the issue. So here's this first block. This is just like the cozy. So after these 3 terms, after the pulse, delay, pulse, we have exactly the operators that we had for the cozy spectrum. What were they? We had something that was returned to Z. So this is coherence order 0 after the second pulse. Here we have a transverse 2-spin operator. This then has in it, if we expand in terms of the raising and lowering operators, this contains I plus, I1 plus, I2 plus, I1 plus, I2 minus, I1 minus, I2 plus, I1 minus, I2 minus. That splits into 4 terms, and it's a superposition of +2, 0, and -2 coherence. And I only want the -2 and +2 parts of that in my experiment. Here is a term that is plus and -1. Here is an antiphase term. This is also plus and -1. So after this 90-degree pulse, every level here has an operator associated with it. I'm only interested in the -2 and the +2 coherence. So I have to figure out how I get rid of the others. That okay? The only coherence now I'm interested in, as I said, is this one. I can expand it then in terms of raising and lowering operators. I played a little trick. I added 0 in. And here I added this operator and subtracted it. And that's because I wanted to end up with this sort of symmetric result, it always helps that I already knew the answer. So this term happens to be called double quantum Y operator. This term happens to be called double quantum, should say double quantum X. And it will turn out when I add up all 4 experiments that I'll be able to show that everything will cancel except for this double quantum Y term. That adding up 4 experiments will isolate, by that recipe, will isolate only this term. All the others I can throw away and ignore for the rest of the experiment. The rest of the experiment is applying the next 90-degree pulse. So here is that term. I put it back in terms of the Cartesian operators. Apply a 90-degree pulse. Here's what I'm left with. This is an antiphase operator. It's X phase, so I think of it as absorptive. This is magnetization that started on the I1 spin, and it's going to be detected on the I1 spin, so this is the diagonal. This is an operator that is antiphase. The transverse component is X, so it will be absorptive, but I'm going to detect it on the I2 spin, even though it started on the I1 spin. So this is a cross peak. So I now have diagonal peaks and cross peaks that are both antiphase and absorptive. I've gotten rid of the diagonal, the dispersive diagonal peak. Now the diagonal is the same phase as the cross peak. I don't have to worry about dispersive tails for cross peaks that are near the diagonal. That happened because both terms, both the diagonal and the cross peak, came from this one term. Whoops, keep forgetting which screen I'm going to read on. They both came from this double quantum Y term. Before, the cross peak and diagonal terms were coming from different operators. Now they're coming from the same operator, and that fixes the phase problem. What's the penalty that I paid? Nothing comes for free, or very little comes for free. What penalty did I pay here? This factor of a half means that I've lost half the signal. It'll turn out, if I went back and worked out each of these 4 steps one by one and looked at what was happening, we would see that 2 of the experiments don't contribute to the signal. Their only purpose is subtracting out terms that I don't want to have contribute to the signal. So only half of the scans are generating the spectrum. The other half are just suppressing the other subspectrum. And as a result, I lose a factor of 2. If I don't need to look at the diagonal, my only goal is to count that I have the right number of H alpha signals, I might as well just run a cozy. I don't care about the diagonal, and it's going to be more sensitive. If I have to look near the diagonal, the double quantum filter cozy will let me look closer to the diagonal at a cost of loss of signal to noise. Now, let me say one more thing in before you correct me. There also will be a little bit of simplification because this peak could only happen, we can only generate the double quantum peak if the peak had a coupling partner. Right? So that means any singlets in the spectrum are suppressed. In this case, for example, methionine methyls are always singlets, they're not coupled to anything, but they're very strong peaks on the diagonal. And in the double quantum filtered cozy, they're going to be suppressed. And there's other signals that can be conveniently suppressed singlets. We could do this if we had a 3-spin system. Coherence orders would go from -3 to +3, and then we could imagine doing a 3-quantum filtered experiment, and then we would only have signals from spins that had 2 coupling partners. Any spins that only had 1 coupling partner would be suppressed. And a 4-quantum filtered cozy, there would only be signals from spins with 3 coupling partners. So you can simplify the topology of the side chains by going to the higher order filtering. Unfortunately, each filtering step costs another factor of 2 in signal to noise. So one runs out of signal to noise before long. But if you ever have to assign a protein without labeling, 3-quantum filtered spectrum can be useful. Right about the time I headed off to be a postdoc and learn NMR, it was right before labeling became possible and triple resonance experiments became possible. And it actually wasn't so clear whether one should go off and postdoc with somebody who was developing higher and higher quantum NMR experiments for this kind of simplification of complicated topologies. But because of labeling, higher quantum experiments with decent solution have become less important. Beyond 2 quantum filtering are now less important because of isotopic. The things might still be different than solids. So what were you going to say?
Just to say the obvious, you're adding and subtracting spectra, and you end up with half of this signal that you pointed out. But all of the spectra that you have to add in, of course, contribute to the noise. When you generated the coherence already, that's a factor of 2. You began with 1 coherence and split it into 2. So when you talk about the phase cycling resulting in only half of the signal, I also wanted to make the distinction between you're actually capturing the double quantum signal that's there. If you lost half of it at the moment that you created the coherence, isn't that right?
Right. At the end of the day, it turns out that signal to noise is down by a factor of 2.
Yeah, but it isn't that your phase cycling scheme missed out some double quantum signal. It's that you split your coherence, and that's where you got the factor of 2. Is that right?
Well, you can think of it both ways. You can think you generated a double quantum coherence and then split it in half. Half went to the diagonal, half went to the cross one. But the pure double quantum signal isn't generated in one scan of the experiment. The pure double quantum coherence is generated by adding pairs of experiments. So that's why I had to add and subtract the other operators. So you can think of it as both ways. But the distinction between kind of the mathematics and then how the noise accumulates when you're actually running the experiment can be different. Ann's point in general is true. One sometimes has to think carefully about the difference between the arithmetic and what's happening to the noise when you're actually acquiring transients. So here's some examples. Here's a cozy, and in order to look close to the diagonal, a very strong window function was applied to truncate the dispersive peaks. So we can see this peak, but you can see the line shape is all distorted by the window function. if there were other peaks nearby, that would be hard to resolve. Here, there's a peak near the diagonal. You can see it's a little bit of a mess. Here's the double quantum filtered cozy. The line shapes are much better near the diagonal, and it's much easier to recognize that here's the 2x2 antiphase pattern there. So that's the real advantage of the double quantum filtered cozy. This was invented by Mark Rance, one of my closest friends, when he was a postdoc. And I think it has 4,000 or so citations now. The paper that published this, and it was published in what most people would say was at best a second-rate journal. So every time anyone is putting pressure on people, students to try to publish in the top journal, I point out that the double quantum filtered cozy is in BBRC and has thousands of citations. Now what I thought Ann was going to point out is we are adding and subtracting transients. We record one pre-induction decay, we record the next, and we subtract them or add them. For this to work, the machine has to be completely stable from transient to transient. And I said you would be suppressing the methionine singlet, for example. Well, the methionine singlet is a very intense peak. If there's any variation from scan to scan in stability of the spectrometer, you're going to get subtraction out of that. So phase cycling depends very, very strongly on the stability of the machine. Now, stability of NMR spectrometers have gotten much, much better. If one were to go back to the late 80s, in the literature, you would find that there were papers in which different ways of doing the phase cycling for the cozy or an HSQC or an HMQC, people published papers on different ways of doing the phase cycling to try to find ways of doing the phase cycling that were less susceptible to variations in spectrometer performance from scan to scan. It's gotten better because machines are a whole lot better, but again, gradients are a way of trying to get around this because gradients let us select a coherence order in a single scan. We don't rely so much on stability from scan to scan. And with luck, we have 5 minutes. Let's skip this phase cycling theory for now because that'll take way longer than, as you can see, it'll take way longer than 5 minutes. And just show, here now is the gradient selected double quantum filtered cozy. So now, in between these two 90s, here's the 90 that generates the double quantum coherence. This 90 converts the double quantum coherence back to single quantum coherence so we can detect it. And now, in between, we've added a gradient in order to use the gradient to select for the coherence order. It turns out the gradient can only detect either +1 or +2 or -2. We can't detect them both. And next time, whenever next time is, we'll talk about why that is. But we're going to use the gradient to select, in this case, +2, and then we'll do a separate experiment to detect -2. Now, the gradient takes some time, so there's going to be chemical shift precession during that time. So we have to refocus that with a little spin echo. So we have to insert a 180-degree pulse. And this is called the encode gradient. And then we have to have a decode gradient. And again, that takes a little bit of time, so we have a little spin echo at the end to refocus the chemical shifts that happen during during the time period. And the advantage here is now we can select in one scan. We're not so sensitive to spectrometer stability, and since the water can't achieve double quantum coherence, let me say, most of the time, Ward, as you might know, has papers about intermolecular double quantum coherence of the water, and we have some tricks for that. In any event, at 0th order, water doesn't generate double quantum coherence, so this is also going to generate very good water suppression and becomes an experiment that's useful. For example, amides that are changing rapidly with solvent that we might miss in a conventional experiment where we might be doing presat on the wall. So, oh, I didn't put in the spectrum. These days, all of the basic experiments have gradient versions as well. And particularly for biomolecules, a lot of the coherence selection now will be with gradients because of the fact that you can do this in one shot. The downside is always, as you can see here, the pulse sequence is longer. So there are going to be relaxation losses. There's going to be a little bit of J-coupling evolution. This spin echo won't refocus J-coupling evolution. So there could be some artifacts from evolution of J-coupling that we might have to deal with. Most of the time, what we worry about are the relaxation losses. And one's trying to figure out how to insert the gradients in the least amount of time. And ideally, there's some delay in the pulse sequence that is already there, and you can sneak the gradient in for free, some of the gradients in for free. And you'll see examples of that as we go on. So, say that again? Right, so here, now because we can only get one, it turns out because we can only get +2 in one experiment and -2 in the other, we've thrown another half of the signal away. So now we're down by a factor of 4. The trade-off is the tremendous quality of the spectrum here. So modern spectrometer is pretty sensitive, and the quality, the artifact suppression is so tremendous in this experiment that it's still quite valuable. When we go to now the proteins with labeling, then this loss becomes a very significant problem. And in the very beginning, this was a real downside to using gradients, say a gradient selected HSQC or gradient selected HMCOs. But then a combination of work that John Cabana and I did as postdocs and that Louis Kay made brilliant use of that we didn't recognize at all, meant that you can recover the gradient loss, the factor of 2, in many isotopically labeled proteins, so on HSQC, HMCO, etc. So that all you lose is the extra time for the turns out the pulse sequence has to be made a little longer. So there's some relaxation losses, but those relaxation losses you still gain up to probably 50 millimolar proteins. So we'll see when we start to talk about HSQC and triple resonance experiments how you can regain that factor of 2. But without tricks, yes, the fact that you lose another factor of 2 just because of this picture showing you can't get +2 and -2 there are very, very few free lunches in NMR. Pardon? And, right.
That's not free either.
Yeah. Okay, we'll see you tomorrow.